Hello year 10s and welcome back to mathematics. In today's lesson we're continuing with our topic of properties of geometric figures, and we're going to be actually looking at continuing with the concept of similarity. In the last couple of lessons we talked about similarity in terms of triangles, and we talked about proving similar triangles and applying similar triangles. What we're doing today is actually looking at similarity in general and talking about what happens when we've got similar shapes. But not only that, we're talking about what happens when we've got similar shapes, and we're looking at measurements not just in one dimension, so not just lengths, but we're also looking at similar shapes and seeing how that affects the area of shapes and also the volume of similar shapes. So in today's lesson, we want to be able to apply similarity with length, area, and volume. We want to be able to identify scale factors to length, area, and volume, find the area of similar shapes, and find the volume of similar shapes. So that's for today's lesson. Let's get into it. Now, similarity can also be applied to volume and area and volume. Now, if you remember, when we looked at the topic of measurement earlier this year, we talked about how we could be measuring different lengths and areas, and we could actually measure these in particular units. So, for example, length. We measured length, and we didn't actually talk about this particular idea or this phrase, but we call the measurements that we measure length linear units. Linear units. So, for example, we measured lengths in terms of millimeters, centimeters, meters, and kilometers. I'm going to move this in a little bit. Hopefully that will fit. Oh, let me try that. Move this in a little bit. There we go. One box across. Okay, cool. There we go. And so here we measured lengths in linear units. For area, if you remember, area was when we had to square all of our units. And so this is squared units. And so, for example, we measured things in millimeters squared, centimeters squared, meters squared, and kilometers squared. And so area was measured in squared units. And the final part was volume, which was measured in cubic units. And so here we had millimeters, instead of squared, it was cubed. Centimeters, cubed. Meters, cubed. And kilometers, cubed. Now you might be wondering, why does this all actually have to apply with similarity? Well, what we've looked at so far is similarity in one dimension, so linear similarity, when we're looking at different lengths. When we actually look at finding similar shapes in other dimensions, so when we're trying to look at similar shapes and the areas, for example, or similar shapes and the volume, if we're looking at 3D shapes, what we need to do is actually either for area, we need to square those units, or for volume, we need to actually cube those units. And so here, if two shapes are similar and have a length ratio of A to B. So if they have a length ratio of A to B, that means that length ratio is A to B. And in our lesson so far, we looked at finding the length scale factor. And the way that we did this was, if we have two measurements, so let's say B is the measurement in our large shape and A is the measure, so this is larger and this is the smaller shape. So if we have the measurement of B centimeters compared to A centimeters, we actually found the scale factor, and we did that by doing B divided by A. Now, when we want to actually apply this to area and volume, what we need to do is we need to actually square both of these measurements. So here, for area measurements, that just becomes A squared to B squared. And so my area scale factor is going to be B squared divided by A squared. Okay. And the same thing is going to happen for my volume, but this time, instead of squaring it, it's now going to be cubed. And so this is going to be A cubed to B cubed. And when I want to find the scale factor, that's just going to be B cubed over A cubed. So if we want to find the volume or area of similar shapes, what we need to do is actually we need to square or cube the original scale factor in our original scale factor for our length ratio in order to help us find the area scale factor or the volume scale factor. So here, what we want to do is actually use the fact that area and volume are just squared and cubic versions of the linear ratio or length ratio, and then help us use that for the and then use that to help us find the area or volume of similar shapes. So here we've got a few steps I want to identify. So firstly, find if we want to apply. So this is applying scale factor to area and volume. Firstly, find the length ratio. So what we want to do is just find the length ratio and then find that linear scale factor, length scale factor. So find corresponding side lengths. Then we want to raise the ratio to the relevant power for area or for volume. So what we want to do is just square those numbers or cube those numbers. So square or cube those numbers depending on whether or not we have an area or a volume. Then from there we multiply or divide the measurements by the area or volume scale factor, just like we did in the previous examples in the last couple of lessons. So let's have a go at a couple of examples of this in this over here. So applying similarity to area. Okay, using similarity to find area. So here we get given two triangles are known to be similar. Find the area of the larger triangle. So here we've got two triangles, and if you have a look, we get given that the first triangle has an area of 3 centimeters squared, and we've also got this measurement of 2 centimeters, and in my larger triangle I have a measurement of 5 centimeters. So what we're going to do is, in order for us to find the area of the larger triangle, what we are going to do is we're going to actually use the length scale factor and then work from there up. So here, first of all, we're going to find the length ratio. So the length, let's just find the length scale factor. And so here, if you remember, when we're trying to find the scale factor, we square the two sides. Oh, we don't square it. We divide the two corresponding sides. So here, it's going to be 5 divided by 2, because these are the two lengths I'm looking at. 5 divided by 2. Now, that was for length. So if we wanted to find any other of the lengths, what we did was we just multiplied or divided by this scale factor. However, because we want to actually deal with the area, we want to find the area of the larger triangle, what we want to do is we want to actually find the area scale factor. So I'm going to call it the area SF, short for scale factor. And so what we need to do is we need to square both of these measurements. So here, instead of it being 5 over 2, it becomes 5 squared, because we're dealing with area now, divided by 2 squared. And so I can chuck this in my calculator. So we've got 5 squared over 2 squared. Oh, no, not the right button. Over 2 squared. And we end up getting that we have a scale factor of 6.25. So what this tells me is that if I want to, the area of the bigger triangle is actually going to, bigger shape is going to be 6.25 times larger compared to the smaller one. So therefore, the area of my larger one is just going to be, I take my measurement of my first one, so 3 times my area scale factor of 6.25, and I end up getting 18.75, and because this is an area, it's going to be in centimeters squared. So that's how we can find area using similarity. Firstly, we want to find the length scale factor. So just like we did in the previous examples, we just want to take the larger measurement, larger length, and divide it by the smaller length. Once we've done that, we want to actually work from there and find the area scale factor. So what we want to do is square both the top and the bottom of my fraction, and so we want to square those two measurements. So here, what we did was we squared those two measurements and we found the area scale factor. And then just like we did in the last lesson, when we're applying this scale factor, all we need to do is just multiply it or divide it depending on what the question gave us. Here we have the smaller triangle and we want to get to the bigger triangle, and so we needed to actually multiply it by that scale factor. So 3 times 6.25, which gave me 18.75 centimeters squared. Okay, let's have a go at the next part. Next example. Now the next example, we're going to be looking at volume. So that was, this first example was for area. Let's have a look at what happens when we want to apply similarity to volume. So the two given prisms are known to be similar. They have the similar shape. Find the volume of the smaller prism, correct 2 decimal places. So here we get given that we've got these two measurements, so 15 centimeters and 10 centimeters. So 15 centimeters for my larger prism, 10 centimeters for my smaller one. And they also tell me that the volume of my prism is 40 centimeters cubed. Okay, so what we're going to do, just like we did in the previous one, what we want to first do is find the length scale factor. So what we're going to do is take the two corresponding lengths and just divide it. So here I've got 15 and 10. I'm just going to do 15 divided by 10. Okay, I'm going to leave it like that. Now you could figure out that this was actually equal to 1.5. I'm going to actually leave that. Because from here, what I want to actually do is find the volume scale factor. Here I'm dealing with volume, so I'm going to find the volume scale factor. And if you remember, volume is a cubic unit. So I'm going to actually need to raise this to the power 3. So this is volume is our cubic unit. And so what I need to do is I need to go, actually this is 15 cubed divided by 10 cubed. Here I'm cubing my ratio. So I'm cubing the ratio between my two lengths. And so I need to actually raise it to the power 3 because I'm dealing with volume. So here I'm going to put this in my calculator. So I've got 15 cubed over 10 cubed. And so that gives me 3.375. Okay, so 3.375. So what this tells me is that the volume of my larger prism is 3.375 times larger than my smaller volume. So for this one, if I want to find the volume of the smaller prism, I'm going to actually take my volume of my larger prism, that's 40, but this time because we're going backwards, instead of multiplying by 3.37, because I want to go to the smaller one, I need to actually divide by 3.375. And so here I'm going to go, that's not the right one, not the right button either, 40 divided by 3.375. We end up getting this number. I want this to 2 decimal places, so 11.85. So here we go, 11.85, and the measurement was in centimeters cubed, so I'm going to have cm cubed. Okay, so that's how we can apply similarity to both area and volume. So let's just do a quick recap of what we did here in the steps. When we are trying to find the area or volume of a similar shape, what we first want to do is find the length scale factor. So just like we did with our last lesson, we take the length measurement in one of our shapes and divide it by the length measurement in the other shape. So usually the bigger divided by the smaller. Then once we found the length scale factor, what we want to do is find the relevant scale factor for either area or volume. So for area, what we did was we squared those two measurements. And for volume, we needed to actually cube it. And so once we've done that, we found the volume or the area scale factor. And just like we did last lesson, all we do is just multiply or divide the scale factor to help me find the relevant volume or area. So that's it for today, Year 10. Hopefully that was helpful. And if you have any questions, feel free to send me a message via Google Classroom or email. I'm more than happy to try and answer your questions. But until next lesson, Year 10, I hope you guys are staying safe wherever you are. And I'll see you in the next video. Bye.